question. Guys, all the properties that we've talked about with exponents and with radicals. Actually, moving over there should be better for you.
It was.
We're
transitioning.
Oh, shit.
Oh my gosh. I'm gonna prove tomorrow.
Good, do that. That's all for
Wherever you go.
So today's essential question. Whoa. Not good. You can use a pen. Can I correctly Guys, two essential questions. One, can I correctly apply rational exponent properties? Okay? We've talked about, and I say it over and over again, most of the math that we've learned previously all stays the same. We're just adding to it. Today, it's just very simple fractions, things you learned in middle school, multiplying and adding fractions, and your exponent rules. So stuff from chapter 5, all your rules of exponents. We're just adding in the fraction stuff, and we'll talk about how to do that. It's the same. We can obviously change rational exponents to radicals, so all that applies as well. And second, I've talked about this a little bit. Today we'll learn how to do it. How do I rationalize denominators? Because from now on, every problem we solve, you will rationalize the denominators that are not rationalized will not receive full credit. Okay.
How many pages?
You know what?
I told you something already asked.
They did. Thank you for telling me that.
Can you go back up?
Yes.
Literally said that.
Thank you.
So, simplify each expression. Guys, we've been doing this all chapter, even last chapter. Simplifying expressions. Write your answer in radical form. So, you need to simplify and then read radicals. So, when I'm multiplying two terms, give me the word terms. When I'm multiplying two terms, there's a lot of work dividing. There's a lot of things to look for. If I have the same base, 12 to an exponent, doesn't matter what it is, times 12 to an exponent.
I said one thing. Are you kidding me?
The last person always gets caught. Second person.
I'm done. I'm literally not just bad.
I wish.
We got a whole empty row here if you want to start moving.
Hey, this is good.
Can I?
That seat is taken.
If I have the same bases, guys, I don't have to do anything with those bases. Don't give me, these operations and then 144. All the math I do here stays with the base of 12. So as long as my bases are the same, all I need to work with are the exponents. So that means I'm multiplying my bases with the exponents. And recall when we did, and it's like I think a problem from your test, or at least close to it, x squared times x to the third was what? X to the fifth, you guys.
X to the 5.
They add. When I'm multiplying and I get the same base, okay, I add the exponents. When the exponent is being raised to an exponent, that's when I multiply. So here, I've got the same base, x, 12, 12. So I'm multiplying. So what do you think I'm going to do with each of these exponents? I'm going to add them. So this is 12 raised to the 1/8 plus 5/6. I'm not done, obviously. I need to actually add those. What do I need when I'm adding or subtracting fractions? Common denominators. What's my common denominator here, guys? Good, 24. So 12. So we're going to have over 24. Over 24. My eighth is what? 3 and 20. Good. So I have, as a final answer, 12 23 over 24. Not done. Not done because I need to write my answer in radical form. This is weird, right? But I have this base of 12, so inside my radical is 12. What kind of root is it? 24th root. Bizarre. And the whole thing's raised to the 23rd.
Wait. Don't you have two 12s that are multiplying? You keep those the same.
When my base is the same, Trent, all I deal with is my exponents. Think back when we did this. Did I have 2x raised to the 5th? No. Or I didn't even do an x squared, right? You know, because x times x would be x squared. All I deal with is these exponents when my bases are the same. Only when your bases are the same. Oh, what do you do when they're not the same? Why, look to example B.
Oh, my. Wait, I'm not
Yeah,
Oh. Oh.
yes, this would absolutely be an acceptable answer.
Right there. That's like a lot. Okay.
Just a little fun. So,
Go away. Can I kill it?
no. So 5 to 1/3 times 7 to the 1/4 raised to the 3rd power, ladies and gentlemen. Are my bases the same there?
No.
No. So I can't just go multiplying across and get anything. When your bases are not the same, you want to do one of two things. You want to try and make them the same. Okay, so if that's possible, go for it. And if you can't do that, try and simplify one of your terms down to where you don't even have to worry about it. So because my bases aren't the same, I'm going to wait on this little operation here. And I'm going to distribute that raised to the 3rd power. Okay, I got room up here too. I'm going to go ahead and distribute that. So now I've got 7 or 5 to the first 1/3 power raised to the 3rd. So what do I do with those exponents? I've got 5 to the 1/3 power, right, raised to the 3rd, times 7 to the 1/4, goodness, raised to the 3rd, right? So what do I do with these exponents? I'm going to distribute. Anybody? Christian said it, but I don't know.
Multiply.
I multiply, right? If I have an exponent being raised to an exponent, I'm multiplying. So this becomes 5 to the 1/3 times 3 times 7 to the 1/4 times 3. 5 to the 1/3 times 3 can be simplified as what? Is that just 5 to the first? 1/3 times 3? Is what not good with 5? It did. That guy went there, that guy went there. Yes.
This is so hard. So hard. I couldn't do it, so I just took it. I saw that and looked at quadrant form. That's the right answer. I just want to know before I keep it.
I can't tell you right here in front of everybody.
He probably did.
But, I mean, you can do that as long as you think it, if you think you did it correctly.
Wait. You're saying
You almost did it.
that's what he always does.
You almost did it. Okay. No, right? Because I'm distributing this 5 up. So I'm not done here. The 3 doesn't go to the 5. The 3 just goes to the exponent.
One.
That's all. No, that is when, guys. Any other time, what you just found out is when I had like, if I have a 5x to the second raised to the second. I've got one term here and one term here that it has to go to. This is just 5 to the 3rd being raised, so it only goes to that term. But I mean, it's also going to that 7.
Right.
Right? Okay, continuing. 1/3 times 3. Yeah, 5 to the first. And then 7, I will change it. Yeah, 7 to the 1/4 times 3, guys. What's 1/4 times 3? 3 over 4, right? Which I'm going to change. This 5 to the first is just 5. Now I'm going to go ahead and change this 7 to the 3/4 to a radical, because those are my instructions. Can't tell you how many points we're missing the test from just not following instructions. What kind of root is it?
3.
So 4th root, denominator is 4, raised to the 3rd.
That's your answer.
That's your answer.
Flag.
I need to make some more room here. So 10 divided by 10 to the 2/5. Is this more like A or B? Probably A or B. More like A. How is this like A?
Same coefficient.
Same base. Guys, I know it's expressed in a weird way, Colton, but if I rewrite this like this, do we agree those are the same base?
I agree.
So when I'm multiplying and I have the same base, I added exponents. What do I do when I have the same base and I'm dividing? Subtract. Good. So 1 minus 2/5. 3/5, right? So 10 to the 3/5. I'm not done. I need to rewrite in a radical form. What kind of root is it?
5.
5th root. Hold on. What don't you understand? Next one's nuts. 56 to the 1/4 divided by 7 to the 1/4 to the 5th. Alright, so do I have the same base?
No.
No, I don't. This might, I hope this doesn't confuse a lot of you.
It will.
Up here on B, folks, when I didn't have the same base, I went ahead and I distributed my term, right, my operation, and then tried to change some things to see if, I could simplify, right? So I'm going to do the same thing here. I'm going to distribute this 5. So I'm going to distribute here and distribute here. So 56 over 7 still. And then I've got, what? Is that a 5? I already erased, scratched over it. So 5. 5 times 1/4. 5/4, right? And then 5 times 1/4 from the bottom as well. So I've got that, guys.
Whole bunch of yeah.
Huh?
Whole bunch of little stuff.
Right. Here's what I'm going to do, folks. Does 56 over 7, does 56 over 7 can reduce, can it? 8. If I pull this down as, and this might help us see it, 56 over 7 to the 5/4 like that, all I've done is pull that out, right? And 56 over 7 can change to 8. And now that's much easier. I'm going to change that to my radical. What kind of root is it? A 4th root raised to the 5th. Last one. 2 to the 6 times 4 to the 6 raised to the -1/6 power. So first thing, I've got what in this problem? A negative. I like to get rid of those first. All right, so let's do that. 1 over 2 to the 6 times 4 to the 6, all raised to the +1/6. Now that's mucho better. What can you already see about my exponents?
Okay.
So the exponents are the same, 2 to the 6 and 4 to the 6.
That's cool. So, no.
Christian, what do you see about those exponents?
See that they are the same.
Yes, we've established that. What about those? The whole thing's raised to a 1/6. What's going to happen to both of my exponents?
But a 1. But a 1.
What are they going to change to? Colton, what are they going to change to? We got 2 to the 6 raised to the 1/6 power. What is that 2 to the 6 to become? Guys, I'll say it again. Just 1? Good. You pulled that one out. 2 to the 6 times 1/6, that's just 2 to the 1st, which is just 2, right? Same with 4. 4 to the 6 times 1/6, that's 4 to the 1st, which is just 4. 2 times 4 is 8. Thank you. That's your answer. This one was weird. You don't always have to get rid of the radical here. This one was just easier to get rid of the radical. I didn't do on any of the others, did I? Every single other one I left as a radical. Even if I say right answer in radical form, if you can simplify, please go ahead and do it. Okay, hold on, I gotta erase this. So, simplify each expression, write answers in radical form. Guys, is this the exact same question? Exact same words. This time I'm dealing with radicals. So there's 2 things to really remember when I'm dealing with radicals, okay? I want to look to see if my indices, which are the root, the number root I'm taking, so chatty. So chatty. I don't want to split this up. So I want to see if my indices are the same. Guys, simple trick. If I've got the same root being taken, I don't care what's in the middle, right? This can be combined to what you do? Just 12 times 18, right? Which is, I think it's like 216. It is 216. This would be acceptable. I'm all right with this answer because it said to write it in a radical form. Hopefully, though, you started building a little bit of number sets. And maybe you can tell me what the cubic root of 216 is. It is 6. If not, or if you just want to, if you want to check and look on your calculator, that's totally fine. That's what the calculator's there for. So. Same thing here, guys. Are my indices the same?
You better believe it.
Yes. So, cubic root of the big old number.
1,000.
Straight up just 1,000?
Yeah.
Nice. Anybody want to take a stab with cubic root of 1,000? You just got 1,000. 1, 2, 3 zeros.
10.
10 times 10 times 10, right?
Come on, G.
Again, folks, if you got to here and you just left it, I am okay with that. Here, not later on. Here I'm okay because all I asked you to do is simplify and write it in a radical. Here's where we get a little more complicated. You've probably seen something like this. Okay, cubic root of 104. Christian, are you plugging it in?
Yeah.
Just tell me what you get.
I got 4.7.
So not a perfect cube, right? There's no perfect cube for 104. But I want to simplify it. What I want to do is break this into numbers that contain perfect cubes, okay? Using multiplication, right? So 104, think about your perfect cubes you know. What's 2 cubed?
8.
8, so 8's pretty far off, but I might be able to divide that by 8. What's 3 cubed?
Not 27.
27, so 27 might work. 4 cubed is 64, but 2 times 64 is not going to work. So I'm definitely looking at either 2 or 3, so either 8 or 27. So just 104 divided by, Christian, what do you want to do, 27 or 8? 27. 27?
Doesn't work.
Doesn't work, so how about 8?
13.
8 and 13. So 8 times 13, you guys, is 104. So if I split this up the way I combined this, the cubic root of 8 times 13, 13 is what? What kind of number is prime? It's prime. It's only divisible by 1 in itself. So it's not going to be able to cube root, but you know the cubic root of 8. It is 2 cubic root 13. So when I have numbers that I can't just take perfect roots of, 4th root, 5th root, whatever it is, split it up into a number you know the perfect root of. Alright, the cubic root of 250. I'll tell you, you can check me though. Yeah, it's not. What?
Why are you looking at me like
Oh,
that?
6.3. I thought you said it was 23. Like, what is wrong with your calculator? Weird. So, not a perfect cube. Long story short, not a perfect cube. Alright, so go through your cubes. We know 8. We know 27. We know 64. That's 4. What's 5? 125. Ooh. What's 250 divided by 125? Duh. Okay. So if I split this up as the cubic root of 2 times 125, what can I pull out of there?
5.
5, right? So 5 cubic root 2. This one I put on there because, I don't know, I felt like making a point again. What can I do with these? I can combine. Why can I just combine and multiply these? They have the same index of 4, right? So this is the 4th root of 27 times 3, which is the 4th root of 81. If you leave it like that, that's okay. Or what can I change that to? I would hope at this point you would see that 27 is perfect cube, and if the cube of 27 is 3, well, if I'm going to multiply that again by 3, that's just 3 to the 4th. If I'm taking a 4th root, fun time, rationalizing the denominator. By fun, I mean
Nuts.
it's not fun. So guys, rationalizing the denominator. This is the process, and it's not really a process. The process makes it sound like it's a bunch of steps and we have to do this every time. I wouldn't call it a process, but it's the process of eliminating elimination? It's the process of eliminating radicals from the denominator. The entire thing. No, we're just doing a few pages. We're going up to 6.4 today. Or no, it's 6. See, you can't talk to me while I'm writing, because then I can make So this is the process of eliminating radicals from the denominator.
Is there an exclamation point?
It's that's the no, it's the G from the thing.
Oh, wow, that really
That's
looks
so
like
exciting. It does look. It's because Gigi was talking to me the whole time. I can't write and talk and listen or anything. I can't multitask. It's why I can't do anything when you guys talk. It's not just because it's disrespectful. It's because I literally can't teach. So, obviously, I can write. Process of eliminating radicals from the denominator. All right, guys. The way I do this, I'm going to multiply by an expression. And remember I'm going to stop there. Remember your rules of algebra. Anytime I multiply by something, what does it have to be equal to?
What?
If I want to alter, do some algebra to an expression or the sides of the equation, it's got 1, right? It's got to be just equal to 1. So I'm going to multiply by an expression. That forms a perfect root in the denominator. Big words, but I'll show you. So the 5th root of 7 over 8. This, you're tempted to say, well, that's over 1. So there's no radicals in the denominator, so that's rationalized. Yeah. Yes, so I would change this, guys. What this is actually saying is the 5th root of 7 over the 5th root of 8, and that's not okay. Why? It's not rationalized. There is a radical in my denominator.
Oh, man.
So what I want to do is get rid of that. And the only way to get rid of a radical completely, guys, hold on. The only way to get rid of a radical completely is to actually have a perfect root inside it, right? Otherwise, I'm just pulling things out, and so it's 2 times a smaller root, right? But to get rid of it completely, I need a perfect root. So, does 8 have a perfect fifth root? No. What are numbers that do have a perfect fifth root?
3.
Well, we'll go up. So, what's 2 to the fifth? 16. Okay, so I can do 16. The next one up, what's 3 to the fifth?
243.
Actually, no, 2 to the fifth isn't 16, it's 32.
32.
So 32 is good. Is 32 divisible by 8, guys? How many times? 4. So if I multiply, I want to multiply this 8 by 4, right? So if I have to multiply by an expression that equals 1, so root 4, root 5 of 4 over root 5 of 4 is 1, right? Guys, here's the big thing. You have to keep this as root 5. Otherwise, if my indices aren't the same, think back to what we just did, I can't multiply these. But as they are, I can combine them. So my numerator, 7 times 4 is what? 28. And 8 times 4? 32. And the reason we did that, because the fifth root of 32 is... What's the fifth root of 32, guys? 2. 64. That's rationalized. As you keep, we'll do some more, and you're going to see that your numerator starts to get ugly. It doesn't matter as long as you don't have radicals in the denominator. All right, so we'll split this one up. So I need to get rid of, and honestly, guys, I would not even worry about your numerator.
I'm worried
in places like this. You just look at the denominator. So the fourth root of 27. I need that radical to go away. Well, 27 is a perfect what? Cube. It's 3 cubed, right? So I'm 1 3 away from having a perfect fourth. So what am I going to multiply by? It's going to be a root. What, root 4? What's going underneath? What do I need to multiply 27 by to have a perfect 4? 3. Okay, leaving me with the fourth root of what? 30, right? 3 times 10 over the fourth root of 27 times 3, folks? 81, which I'm going to change to what?
3.
Rational. Notice, I didn't even think to point this out, these 3 examples, what are the directions here?
Write the expression in the interval as radical form.
Notice that simplifying radicals now, or simplifying expressions, also includes rationalizing. So if you've simplified something but you don't take the next step and rationalize it, not full points. Rationalizing and simplifying are now synonymous, they mean the same thing. Alrighty here. Fifth root of 96 over the fifth root of 3. Here's what's easy about this one, guys. The fifth root of 3. 3 is already a prime number, right? So I just need to multiply that by itself 4 more times, and I should have a perfect fifth root, right? So this guy times, and we're going to have a fifth radical over a fifth radical. So I need to take 3. I've got 3 to the first, right? 3 to the second, third, fourth, fifth. So what is 3 to the fourth? Hint, hint, look right above the problem we just did. 81. 81. 81 times 96. That's a big number.
7,076.
7,776. Guys, I don't care how ugly your numerator gets. You just got to rationalize the denominator. All you got to do. So 3 times 81.
243.
243, which I'm going to change to what? I'm going to change to 3.
So is it always going to be what the original number was? In the radical?
Was it here? No, not always. Only when your starting denominator in the radican or in the radical is already like the root you want. So just so you know, 776 is a perfect fifth root. Yeah, 6. So if you wanted to change that to just 6, you could, and you would change that to 2. That one, you do need to go to the next step. Because my instructions were simplest radical form, and if something's a perfect root, you really need to simplify that. So just check, it's not hard. Last one, do D on your own, guys. Try D on your own. It's very similar to the one we just did. D on your own. Not bad at all. Yeah. So, got a 50, one that 50 radical to go with. You gotta ask yourself, what do I need to multiply my radical? What do I need to multiply that by to make it a perfect fifth root? And I knew that 243 was a perfect fifth root. Right? So I just need to multiply by something here. So that is where that's you need 4. Yeah. So that's what you
I don't know how to explain it. Because 1.5 I know how to do it.
you want to get multiplied by something so that you get a perfect. So what are you going to multiply by? So what's nice about 5 is it's really multiply by nothing. What you multiply by? Only when your numbers small like prime numbers. Last one we did was the ones before were small prime numbers, so like 27 and stuff. But we still do. I was looking for like a fourth root, and I had 27. We go 27 for I multiply that by 3 one more time. I got perfect. So. Did I? I didn't mean to. I thought you might have just said 20. It's hard. Well, okay, I thought you were asking. All right, folks. So I need to multiply. We can always set this up, guys. You're going to have a radical, and I know it's going to be a fourth root. I was helping people over here who are asking. I hope we all just have the answer.
I got the answer.
Good. Okay. Should have asked. Let's go through it though. So I need to get a perfect fourth root. what if I just took the number 5, multiplied it by itself enough times until I got a perfect fourth root? So 5, I'm starting there, that's 5 to the first. So what's 5 times 5? Times 5, 125. So 5 to the fourth is 625. That's what I want to wind up with. That's not what I multiply by, but that's what I want. Okay, so if you want to think, well, I want to wind up with 625. That's what I want to end up with. Okay, because that will change to just 5. Okay, so what do I multiply by here?
80 or 80.
125.
Thank
So what's 80 times 125? 10,000. Do you think 10,000 is perfect fourth?
Oh, man.
That's 10 to the fourth, guys. 1, 2, 3, 4 zeros. The little caterpillar. Alright. No. Time to do more.
Are you sure?
Adding and subtracting radicals. Guys, a lot of this, guys, your radicals adding and subtracting is just like adding and subtracting variables. Okay? I need to have like terms. When I was dealing with expressions and equations, guys, and it said to combine like terms, I took all the like x squared terms and I counted how many there were, right? If there was a 7 and a negative 3x squared, I would make that a 4x squared, right? All that stays the same here. If two things are the same, guys, I need my index or my root. That's just what root I'm taking, okay? And my radicand, okay, which is the number underneath the radical, okay, to be the same. So look at A. Are my indexes the same?
The root.
The index is my root. So my index,
What's the last word say?
radicand.
Why don't you use it? Is that a plus?
It's not better.
Plus?
And that's an and symbol. It's an ampersand.
Oh.
I don't know. Gee.
Yeah. How would you use your pen? How would you try to use your pen for once?
Are my indices, the plural index, are they the same? Yes. Do I have the same radical?
No.
Yes.
Yes.
So this is asking me, guys, this is asking me, how many fourth roots of 10 are there?
7. Oh. 8.
There's a 1 there, right? So I can just add these. There are 8 fourth roots of 10.
Not the answer.
They're all like that, right?
Okay. If your
That's it.
if your index isn't the same, we'll talk about that much later. We're not going to worry about that. But if your radicand isn't the same, you need to make them the same, guys. So my indices are the same here. So I've got something to work with. I can't just subtract, though. Right? I need to make this so they're all talking about the same term. Well, are either of these perfect cubes? No, they're not. Are they? Either of them have common factors?
Yeah.
Yes, they do. What are they? They both have a factor of 3. So what's 81 divided by 3?
27.
27. What's 24 divided by 3?
8.
8. So I'm going to break both of these down, guys. I've got a 27 times 3 and an 8 times 3. What's nice about those? What can I pull out of both of those? Well, the 3 is going to stay the same because the 3 is not perfect. Is 27 a perfect cube?
Yeah.
Is 8 a perfect cube?
Yeah.
What's the cube root of 27?
3.
3 cube root of 3 minus, what's the cube root of 8? 2 cube root of 3. Now, Are my indices the same?
Yes.
Are my radicans the same?
Yes.
They're both 3, right?
Yes.
So how many cube roots of 3 are there? 3 minus 2?
1.
1 cube root of 3, which no, absolutely do not. So cube root of 5 plus a cube root of 40. Are my indices the same?
No. Wait, yes.
Yes, they are. They're both cube roots. 5 and 40, are those the same
No.
number? No, but I need to make them the same. Well, I know I can't change 5 at all, can I?
No.
So I'm probably going to work with 40. Can I get a 5? Can I make this to get a 5 underneath?
Yeah.
Who's got some ideas? Christian, what do you think?
Well, I think
Yeah.
we should divide 40.
5 and get what?
8.
Good. So Christian's got a great idea, guys. I'm gonna make some room.
You can't tell if you're being sarcastic.
No, it's good. 5 plus the cube root of 5 times what? Trent, now what? So I broke 40 into 5 and 8, 5 times 8. Can I pull anything out of that? So you're saying I can pull this cube root out. So leaving me with, I've got a cube root of 5 plus 2 cube root of 5. Colton, then what? This is kind of all we're doing, guys.
Gotta add 2 and 1.
Colton, are my radicans the same?
Oh, yeah. 1 and 2.
They're both 5. Okay. Are my indices the same? So what do I do with these?
Add them.
To what?
3.
3 cube roots of 5. All it's asking me is how many cube roots of 5 are there. I know I've got 1 here and 2 here, so there are 3. This last one's super fun. This one's not written in radicals, it's written in rational exponents, right? Okay, so go back to this first problem. I had 4th root of 10, of root 10, sorry, 4th root of 10 plus 7 4th root of 10. So it was asking me how many 4th roots of 10 are there. Here I've got 4 times 9 to the 2/3 plus 8 times 9 to the 2/3. They're both the 2/3, but they're both what to 2/3? 9. Remember, guys, with order of operations, I'm not carrying this 2/3 for this guy. I've got parentheses. I could honestly write my parentheses here and it'd be the same, right? Is this just asking me how many 9 to the 2/3 are there? How many are there?
2. Wait, what?
12, 9 to the 2/3. I've got 4, right, of these, and then I've got 8 of these. If I change them to radicals, it might be easier, right? So I've got 4 times the cube root of 9 squared plus 8 times the cube root of 9 squared. Now do we see it? Now does it look like this guy up here? 4th root of 10, 4th root of 10, 3rd root of 9 squared, 3rd root of 9 squared. If you wanted to change the 9 squared, what would you change it to?
81.
Yeah, you can go ahead and change that to 81, that's fine. Now it's even clearer, right? Those are absolutely the same. So 12 cube roots of 81. Either one of these is good. Okay.
That's the answer.
It's a simple radical form. So
Yeah, one's even simplest radical form. I wouldn't be okay with this. Why, Amelia? Why am I not okay with this?
What's the top answer?
The top because I'm not in radical form. Okay, and why am I not okay with this? I can simplify cube root of 81. Is 81 a perfect cube? No. It's not. It's a perfect fourth, right?
Yeah.
The fourth root of 81 is 3. But can I break this down into 12 times the cube root of 3 times 27?
You better believe it.
What's the cube root of 27? So 3 times 12 is 36. Cube root of 3. That's the simplest route.
Are we done now?
Nope.
Great number.
Hey guys, I don't want to do all of these, all right? Partially because you just did this on your homework. The only thing you almost did this on your test, you just didn't have radicals, right? I've told you the easiest way to handle these problems is to split them up. So I want to go to D and just make sure we're all good there. I would do this, unless you're just really good at seeing this and you know you got it, I would do this every time. I still do it a lot, right? I would split these terms up, all right? So this is actually the cube root of 6, okay, times the cube root of x to the 4th times the cube root of y to the 9th times the cube root of z to the 14th, right? And from there, we can work with it in terms of simplification. The cube root of 3 to the 6, or cube root of 6, I'm not going to be able to change. So that guy is just going to stay. Cube root of 6. So I know I'm going to have that everywhere. If it helps you to rewrite these, that's the please do, right? Yeah, x to the 4th. Yeah, my bad. We're good. Remember when you're doing, how do I explain this? When you're doing radicals of, like, cube roots of exponents, guys, these just get subtracted. And that's great when you've got flipped and your big number is your radical, is your index. But I don't have that here. So I can actually only pull out 3. So the cube root of x to the 4th, I actually will change to x, and then it's the square root of x, or sorry, cube root of x. But I can only pull 3 of these 4 out, leaving me with 1 underneath. So it's the same thing here. The cube root of y to the 9th. How many can I pull out of there? 3, because it's a cube root, right? So cube root of y to the 6th. But I can actually keep pulling out of there. So then I can pull out another y, right? So y times y.
You just put y the second.
Hold on, yeah. Cube root of y to the 3rd, right? I can do it again. And then I can do it one more time. What's the cube root of y to the 3rd? Y. So y times y times y. Y cubed. If you saw that y to the 3rd times y to the 3rd is y to the 9th, if y times y is y to the 9th, then that's great. But if you didn't, that's fine. So then, how many the cube root of z to the 14th? How many can I pull out of there? 3, but this is, guys, do we agree that this is the same as the cube root of z to the 12th times z to the 2nd? If I will simplify that, so then I can pull out how many from that z to the 12th? Right, that's just z to the 4th, right? So I'm going to change this to cube root is equal to 7. So then if I multiply all these together, so I've got this x on the outside, I've got a y cubed on the outside, I've got a z to the 4th on the outside, and then everything's still under a cube root, 6x z to the 2nd. All your rules of exponents, all your rules of radicals stay the same, guys. The only thing that we've added was throwing in all these cubes and everything. Should we do another one?
Is number x cubed too?
What?
Actually, no. Oh, I never.
No.
Yeah, I just looked at it.